So, good morning, everyone. I think it's time to get started. Today, we're going to look at programming from a psychological perspective. And I've been looking forward to this presentation because it's been almost more than 10 years in the making. So let me tell you what happened 10 years ago. At that time, I just joined a new project. And that project had been going on for a while, a couple of years. And it was a fairly large project. We had something like 50 to 60 developers working on it. And during those years, they had developed a bunch of new subsystems. And now, as I joined, there was only one thing left to do. I repeat, only one thing left to do. And that was to integrate it. So I joined, and we somehow managed to bring all those years of development effort together and get it up and running, at least for a couple of milliseconds. And then it crashed, and it crashed brutally. So that bug was eventually found, and we got the system up and running again, and it crashed again. And that cycle repeated for more than 6 months before we finally had to just pull the plug and redesign large parts of the system to make it work at all. Now, thankfully, this was nothing important, just a piece of vital, safety-critical software. And that's kind of my point, that those developers, they were really, really good programmers. And yet we failed to bring it together. And the takeaway for me was that software is somehow different. Software is just so hard to reason about. I mean, there's no way that we can pick up a large, complicated system and just reason about it. We just don't know, is this the final bug? Will there be 10 more bugs? Or will it never, ever work? Software is different. And I wanted to understand why software is so complicated. And I decided to seek those answers outside of the programming discipline. So that's when I started to study psychology. And I think that psychology has a lot to offer in this traditional technical area. Because as developers, our primary tool isn't the machine. It's not the compiler, it's not the IDE, it's the brain. And psychology is about how our brain works. It's how we think, how we reason, how we solve problems, and also how we work together. So I think that psychology has a lot to offer. And what I want to do today is to take some of the stuff I learned during my years in psychology and bring them back to programming. So this is the agenda for today, and we are going to cover a bunch of different topics, all of them somehow related to programming. So let's get started with the first one. Let's get started with beauty. And I'm of the firm belief that beauty is one of the most important tools we have when we program. And when I started to study beauty, I was quite surprised, because I knew that beauty affects us. What surprised me was how strong that effect is. It turns out, just to give you an example, think about attractive people. If you meet an attractive person, you will automatically consider them not only to be more friendly and social, but also more intelligent and competent based on appearance alone. This isn't fair, but it's good news for us. So it turns out that beauty is not just limited to people. The same holds true for machines or physical objects. And one of the best research studies done on that was by a bunch of researchers that studied ATM machines. Plain old, boring ATM machines. And what they did was, they took 2 machines, identical, and then they pimped one of the machines, just to make it look a little bit prettier. And it turned out that people reported that that pimped machine, it was so much easier to operate, it was so much more user-friendly. And the only thing that differed was the surface. It looked a little bit prettier. So there's your usability hack. And it also means that if we want to write code that's easy to understand, we need to write beautiful code. What is beautiful code? What is beauty? We're going to find out together, and we will do that by repeating a classical study in the psychology of attractiveness. So this is a classic experiment, and I'm using the real data here. And your task now is that what will happen is I will present a number of faces here. And your task is to select the face you find the most beautiful. All right? Let's go. Just pick one of the faces. If you're like the majority of all people that do this test, you have picked a woman in the upper left corner. Here are the bad news if some of you hope to ever meet her. She doesn't exist, and she never has. That woman is a composite of all the other photos. And this is the surprising thing that the researchers found out when they started to do this experiment. That they found out when they took photos of individuals and started to combine them together, the more photos they combined, the more attractive the end result became. And it's surprising because what happens when you combine individual photos is that individual differences disappear. The end result goes towards an average. And that must mean that beauty is nothing but average. It must also mean that our average code base, that's beautiful code, right? I don't think you agree with me. Strange. Well, it turns out that beauty is indeed average. But beauty is not average in the sense of common or typical. No, beauty is average in a mathematical sense. And that's indeed a rare thing. So you can pretty much witness that here. You see, they have quite average features, and they are quite symmetrical. And these are some more modern composite pictures. So it turns out that beauty is not so much about what's there. Beauty is about what's absent. Beauty is the absence of ugliness, which, interestingly enough, makes beauty a negative concept. Now, why is that so important for us? Well, it probably has evolutionary reasons. If you look at life from an evolutionary perspective, we have one single task in life: to reproduce. And that means that evolution, what's important for evolution is that you find a partner with good genes. How do we do that? Well, back in the Stone Age, DNA tests, they were pretty tricky to come by. Today, it's doable, but it's something I don't really recommend. Don't try that on a first date. It won't go well. I'm talking from experience here. So what we came to do instead is that we came to use beauty as a proxy for good genes. And the reason for that is that if you grew up to have average symmetrical features, that probably means you have a strong immune system. A strong immune system that protected you from infectious diseases. So beauty is indeed a proxy for good genes from an evolutionary perspective. And interesting enough, this definition of beauty as the absence of ugliness, that's something we can use when we reason about software as well. Because what's ugliness in code? I would say it's everything that puts an unnecessary load upon our brain. So you have things like explicit conditional logic, explicit loops, or when it comes to architectures, you have things like inconsistencies. All that ugly stuff. And during this presentation, we get several opportunities to witness that kind of code. So let's continue with working memory. The human mind has a bunch of different memory systems, and working memory is just one of them. Working memory is a short-term store, but it's much more than that. Working memory is more like a mental workbench of the mind. It's working memory that you use to integrate and manipulate and reason about things in your head. So it's working memory that you use when you do crosswords, or when you try to solve a Sudoku, or when you try to reason about a method in C#. So working memory is vital to us as developers. The bad news are that working memory is also a strictly limited cognitive resource. There's really just so much we can hold in our head at once. And traditionally, within psychology, it's been said that we can only hold 7 things at a time in our head. Modern research paints a much darker picture. Depending on the kind of information, it may be as little as 3 things. 3 things at a time in our working memory. Think back to a last class you wrote. How many instance variables did you use? More than 3? It's not a wonder that things go wrong sometime. But fortunately, there's a workaround we can use to stretch the capacity of our working memory. And it's a workaround we can learn about by studying chess masters. Now, chess masters, they can do amazing things. They can play chess simultaneously with 20 different people. And at every given time, they know the precise positions of the pieces on every single board. I mean, there's no way I can do that. I think it's quite amazing, actually. But try this. Take a chessboard and rearrange the pieces. Put the pieces in an order that could never occur naturally. For example, both bishops on the same color. Now, the chess masters, they won't perform better than you or me. Because their memory isn't necessarily better, it just works differently. It turns out the chess master, they don't remember individual pieces. They remember patterns. They remember groups of pieces. They use a technique called chunking. And I would like to demonstrate chunking to you. And I want to demonstrate it by having you do a small experiment. So what will happen now is that I will present a long string of characters here. And your task is to remember as many characters as possible. And see if you can make it past 7, right? So, are you ready? 1, 2, 3. Oops, a little bit too fast perhaps, sorry. Let's do it one more time. Ready? 1, 2, 3. All right. So it's my guess that it was a little bit easier the second time around. And I also think that most of you noticed that it was indeed the same characters. I just choose to group them differently. I choose to group individual characters into words. And words, in this case, are chunks. You can still just hold 7 things at a time in your head, but now each thing carries more information. So chunking is a technique to stretch the capacity of your working memory bottleneck. How can we use this when we program? Well, the most fundamental chunking mechanism we have in programming is the humble function. So let's have a look at that. What you see here is a piece of open source code. This is code from a Minecraft server. And the only reason I picked this code is because I wanted something natural, something that we can come across in our daily work. And I also like with this code, it's pretty typical server functionality, right? You see here, we're entering an eternal loop, and inside that loop, we're iterating over a bunch of connected clients. And then we let each client perform some kind of periodic I/O task, whatever that is. It isn't really important in this case. And to me, this kind of sounds like a chunk. So let's introduce a function to represent that. Then the next piece of the code here, it actually took me a while to understand what's happening there. But it turns out that's just the server keeping track of the overall playtime. So let's chunk away that as well. Now, you see that we are calculating something with a different time here. And that's just the time until we should do a total refresh of the connected virtual world. So let's chunk that away as well. And when you get to the bottom, you notice something interesting. Fred, sleep, 10. That can never be a good thing. But I would like to put a name on that too, but I don't know why it's there. I can guess, but I don't understand it well enough yet. So I'm going to leave it as it is now, and perhaps we're going to come back to it later. What I want you to do now is to focus on the overall pattern here. So we have this code. Have a look what happens when we introduce those chunks. We move away from this to that. Now, this is much simpler. This is code that fits my head. This is code that I can reason about, code that I can understand, and as a consequence, it's code that we can improve. And that, quite naturally, leads us to our next topic, which is serial killers. Now quick, what do serial killers and Erlang programming have in common? As far as I'm concerned, absolutely nothing. But for serial killers, they are relevant. This is a story about a guy named Thomas Quick. And Thomas Quick is from my native Sweden. And Thomas Quick is quite famous in Sweden because what happened was that in the early 90s, Thomas Quick received psychotherapy. And during that therapy, he started to confess to a lot of brutal murders. All of them well-known, unsolved murder cases. And Thomas Quick, he confessed to as many as 30 murders. And he was eventually convicted to 8 of them. There was only a problem. Thomas Quick never killed anyone. He was innocent, and it was proven beyond doubt. And he got acquitted, and today he walks the streets as a free man. Now, as a psychologist, I got quite interested in this case, so I started to read up a lot about it. And I wanted to understand, first of all, why was he convicted? But more interestingly, why did he confess to something that he obviously hadn't done? And it turned out that there were a lot of things that played in, but first of all, he was on heavy medication during his psychotherapy, which helped to make him more suggestible. And Thomas Quick, he lied a lot, obviously. He liked the attention that it gave him. But there was more to it than that. There were times where Thomas Quick believed his own stories. He was convinced that he was a serial killer. Thomas Quick had developed what psychologists refer to as false memories. And a false memory, it really sounds like a paradox, doesn't it? But it's an everyday thing. It's something that happens to you all. A false memory, it's just a memory of an event that has either never happened or at least not happened in the way you remember it. Your memory is generative, it's constructive. It doesn't work like a movie or a photo. So within psychology, false memories are my specialty. That's what I find the most interesting, and that's where I've done my research. So when you research false memories, it's a little bit tricky. The best thing to do would be if we could use the same psychotherapy methods that they used on Thomas Quick. The problem with that is that it's expensive, it's time-consuming, and it's also slightly unethical. You know, if you take part in a study on false memories, I don't want you to leave and believe you're brutal serial killers. It's just not a nice thing to do, is it? So, fortunately, we get some other methods to study the concept. If you take part in a research study on false memories, it's quite likely that you will see the following. So you will be presented with a list of words, one by one. And it will be words like this, typically: bed, awake, tired, dream, and so on. And after you have seen all those words, one by one, you will be asked to write down as many as you can remember. And now something really interesting happens. A lot of participants write down a word that has never been presented. And it turns out it's the same word for everyone. In this case, with a list like that, the word is sleep. You have developed a false memory for a word that has never been presented. And this, it sounds really simple, right? And that's the beauty of it. This is a simple way to study a very complex phenom. And it turns out there's a strong correlation between your performance on this task and your tendency to develop false memories in real life. Now, I think that you're probably all wondering, how is he going to tie this back to programming? And yes, I'm a little bit curious myself. So let's have a go at that. This is relevant to us as developers because it tells us something about our memory. It tells us how our memory is organized. Because the reason this illusion works is due to implicit associations between semantically close words. Your memory is hierarchical. Your memory loves to put categories and labels on stuff. So the takeaway is, if we want our programs to be easy to understand, we must find a way to categorize our design elements. How do we do that? We have things like functions, we have classes, some languages even have module systems. But all of those are fairly low level. That's not what I'm after at all. And in fact, I only found one single technology that has something that's reminiscent of where I want to go. So I would like to show you that as an inspiration. This is Erlang. So let me ask you, do we have any Erlang programmers in here? None. Cool. Let's see if I can convince you to give it a try. Now, Erlang is interesting because if you attend a technical session on Erlang, what you will hear about is all those technical advantages. Erlang's ability to scale on multi-core, distributable, and it's fault tolerant, and it's fast, and it's, yeah, all those technical aspects. To me, I mean, those are true, but that's not the interesting thing with Erlang. The interesting thing with Erlang is how programs are organized. Because it turns out Erlang programs are always organized according to a number of patterns. And first of all, you see that Erlang programs are hierarchical. And at the bottom, you have something called a worker process. Everything is a process in Erlang. So a worker only does one single thing. It does application logic. Now, let's take our beauty tool and apply it to worker process. What's absent from a worker? Well, let me tell you. There are no special cases. There's no error handling. A worker process only expresses the happy day scenario. And when things go wrong, the worker simply terminates and leaves the control to supervisor. Now, a supervisor knows one single thing. It knows the error handling strategy. So a supervisor can choose to either just restart the worker or perhaps terminate all workers or terminate itself and leave the control to the next supervisor. And the interesting thing with Erlang programs is that they make it so much easier to mentally navigate a complex system. Because now I know in Erlang that if I want to know what the error handling strategy is, I know there's only one single place to look in a supervisor. It's not like my C# code where the error handling strategy is smeared around in 50 different classes in try-catch blocks. So Erlang, with its structure, really simplifies software. Your brain loves Erlang. You didn't know that, did you? All right, let's talk about something else, but something related. Let's talk about attention. Attention is related to working memory. Because for us to be consciously aware of something, we must focus our attention on it. So attention is vital to us developers as well. And just as working memory, attention is a strictly limited cognitive resource. In fact, you can only be consciously aware of one single thing at a time. And it's quite easy to demonstrate that. Have a look at this object here, this cube. It's the kind of object you will never find in real life. Why is that? Well, this object, it lacks textures. There's no shading, no light, and the consequence of that is that your visual system doesn't get any hints. And that's why we're able to fool the brain. And we're able to fool the brain into seeing it in two different ways. So if you practice a little bit, you will be able to switch between those two ways of seeing it at will. But I promise you, no matter how much you practice, you will never, ever be able to see both representations at the same time. It's just a fundamental limitation of our brain. We can only be consciously aware of one single thing at a time. But is that really true? That's a different kind of attention as well. And we can learn about that attention by attending a cocktail party. How nice isn't that? Now, think of yourself at the cocktail party. You're entering this party and you meet someone you know. So you strike up a conversation. And you start to talk to someone. At the same time, there may be literally hundreds of conversations going on around you. And if I were to interrupt you at that moment and ask you, what were the other conversations about? You just don't know. You have been focusing on your conversation, so you have no idea what the other people were talking about. But say that this happens. You stand there and you have a conversation, you chat with your friend, and suddenly someone mentions your name, like Adam. Yes? Wow. What just happened? We said that we haven't heard a single word, but as soon as someone mentions our name, our attention is drawn away, almost like a magnet. What's happening? Well, it turns out, and this is indeed one of the few things that Sigmund Freud got right. It turns out that the majority of your brain activity is unconscious, or automatic, as they say today. So at any given moment, including now, your brain, you have a lot of unconscious processes that scan the environment, scan the surroundings for information of personal relevance, like, for example, your name, one of the most important pieces of information to you. So as soon as those automatic processes detect some relevant information, your attention is directed there, where it's likely to be needed. Now, this is a trick that we can use when we program. So let's return to our Minecraft server. This is the code that we refactored earlier. And I have to say it looks much better. It's quite pretty, actually. Perhaps a little bit too pretty. Because we're hiding away a lot of ugly stuff here. Have a look at this. This is the code when we iterate over the clients. But before we do that, we acquire a lock. Now, let me tell you, lock-based concurrency is always a problem. Locks on that level is definitely a problem, right? So when I see something like that, I want to redesign it. But I also know that multi-threading is just so hard to get right, so this will probably take some time to redesign. So what I want to do in the meantime is to somehow raise some kind of mental warning sign that says, hey, watch out, tricky stuff ahead. Now, given what we just learned about attention, we actually have a way of doing that. So what I do is I take this pretty code and I introduce a surprise. I introduce a little bit of ugliness into the program, something that breaks our expectations, something that breaks our flow, something that is likely to serve as an attentional magnet. So this is like a mental post-it on the code, watch out. And I have to tell you this, we talked about beauty, and ugliness has this property that it affects our emotions. It makes us feel a little bit sick. And when we introduce ugliness, I mean, that's not really a nice thing to do, but again, neither are global locks, so I think we're even there. So, that was attention. Let's talk about language. And language is my favorite topic, because language, our natural languages, the languages that we speak, they are not just a way to communicate with each other. A language affects the way we think, the way we perceive the word. And we can witness that by doing a small thought experiment together. Have a look at this deep, red, beautiful rose. A red rose like that evokes emotions in us. We think about love. We think about friendship. A lot of positive feelings, right? But now, think for a moment that your language would lack a name for the color red. Would you still perceive that rose as so beautiful? Would you still think of love and friendship? Possibly not. And this is called the principle of linguistic relativity. And the best study I know on linguistic relativity is done on a group of Aboriginals called Gugu-Yimitir. Now, Gugu-Yimitir, by the way, you all know a word in their language. Anyone knows that word? Yeah. Sorry? Yeah, kangaroo. But close. So, kangaroo is their main export, but their language has a much more interesting property. In fact, when they're given when they give directions, they do that as geographical directions. So if you have a conversation with someone that speaks Googie Meteor, they may say things like, "Hey, Adam, watch out. You have a mosquito on your southeast shoulder." "Oh, great. Thanks." Quite practical, isn't it? And as a consequence, they grew up constantly focusing on the geographical directions. And the consequence is that they get quite good at orientating themselves. They never get lost, like I do. But ask them to perform a task that requires a relative orientation, perhaps setting a round table with, knives to the right and forks to the left, and they will actually have trouble with that. So that's good to know that our Western European languages are good for something as well. Now, this idea with linguistic relativity goes all the way back to Ludwig Wittgenstein. And Wittgenstein once said that the limits of my language means the limits of my word. And I mean, it's a cool thing to say. The problem is it's just not correct. A language never limits your word. What it does, however, is that it may influence parts of how you perceive the world around you. So this statement is way too strong. But I don't know if Ludwig Wittgenstein was a good software developer, but I think he was. Because this statement, I think it's spot on when it comes to programming languages. Because our programming languages, they are much more diverse than our natural languages. They are indeed different ways of thinking, completely different ways of seeing the world. And one of the pioneers in that area was Ken Iverson. Back in the early 60s, Ken Iverson designed a programming language, APL. And APL to Iverson, it was not just a way to instruct a machine. APL to Iverson was a thinking tool. And to serve well as a thinking tool, APL needed to have a very compact representation. Does anyone know APL? Oh, cool. No one. So, how compact is APL? Well, what you see here in the speech bubble is actually a complete APL program. And this program, it draws a series of 6 lottery numbers, random numbers, no duplicates, the numbers 1 to 40, and delivers them sorted in ascending order. It's pretty compact, isn't it? How many lines of Java or C# would you need to do that? And the reason APL is so compact is that, again, let's take our beauty tool and see what's absent. You don't see any explicit conditional logic. There are no conditions to start or terminate there. More interestingly, you don't even see some explicit loops, even though it describes an iterative process. And the reason for that is that APL uses arrays as a fundamental data type. And that means that the functions you write, they never operate on individual, they can do, but they rarely operate on individual elements. Most of the time, they operate on sequences of elements. And that means that you can erase a whole vast array of differences. Because now, it doesn't matter to your program if you have 0 or of something, 1 or 1,000. Your code looks exactly the same. And that's really powerful because it helps us get away with we can remove a lot of ugliness from our code. And we're going to return to those ideas soon. But before we do that, we have to talk about something very unpleasant. This is a subject that I strongly dislike. And now you're wondering, all right, so we already talked about serial killers. What could possibly be worse? Well, let me tell you, null references. So the reason I dislike null is because null always means a special case. And you can see that here. Think about this for a moment. Let's take a string as a simple example. So we have a string here, and we can assign a lot of different values to a string. We can even assign it an empty string. We can also assign null to a string. And the moment we do that, we can forget everything we know about strings. We can forget everything in the string API, because nothing holds true anymore. we have introduced a special case. And it's a special case that will ripple through our code and wreak havoc on it. So that's the problem I have with null. And this has been a problem for decades. And this is why the safe navigation operator is one of the most suggested features to C#, and it will actually make it into the next version. And there has been a lot of discussions about adding this to Java as well. So what is a safe navigation operator? It works like this. This is the safe navigation operator, by the way. So it's used to chain together property access like this. And it works this way. If all of those objects are valid, Tricky here gets assigned the value of violating the meter. Now, if something along that chain should be null, the safe navigation operator will short-circuit the whole evaluation, and Tricky will become null itself. So that's why it's safe. And to me, the safe navigation operator is a very elegant solution to the wrong problem. Let's see why. We're back into our Minecraft server code. And we see some code here. I'm not sure if you can read it in the back there. But it's, again, it's just the overall pattern that's important. You see, we have a bunch of null values that we allow here. And first, we have some kind of base directory. It may be null, so we have to check for that. If it's valid, we can create a region file name. We have to check if that's null as well. If it's valid, we can create a file, and from that, a region object, whatever that is. Doesn't really matter. Now, this code is much more complicated than I would like it to be. What I would like to see is this. This is much simpler. This is the kind of code I would like to write here. So the advantage is this code is easier to understand. The possible disadvantage is that it won't work. Because the only thing I've done is that I threw away the null checks. So as soon as something here returns null, the whole thing will blow up with a null reference exception. In general, not a good thing. So we could, of course, catch that null reference and try to do something sensible, but that only makes things worse. Because now we've introduced an invisible, implicit flow of control in our program. And our brains have a terribly hard time to reason about that. It's exactly the same reason that multithreading is hard, right? So we don't want to go there. Let's see what we can do instead. And let's do that by taking a step back. Let's consider the kind of code you would like to write. So this is the code without the null checks. Let's see what we actually have there if we dissect it. You will see that we have symbols on the left, or variables, as you may call them. And those symbols are bound to the results of computations on the right. You also see that the flow of control goes from top to bottom. And as soon as something returns null, well, the whole thing blows up. But what if, just what if, we would find a way to instruct the compiler how to glue those computations together? If we could somehow run code between each line here, then we could have that code to check for invalid values, like null. It turns out we actually have a way of doing that. And that way is called Monads. Does anyone know about Monads? Some of you, cool. Monads are pretty well known within functional programming, most prominently within Haskell, where monads are used for virtually any interesting task. Now, if you Google monads, you will find that we have a whole industry writing monad tutorials. You have everything from the formal mathematical definition to powerful metaphors like assembly lines or even burritos, which is one of my favorite metaphors. But a monad is actually much simpler than that. So this is my favorite definition of a monad. This is a monad. Monads have been called a programmable semicolon. And that, of course, refers to the common line terminator. So you can have a mental model of a monad as some way to program the semicolons. to instruct how the results of one computation should flow into the next line. That's a monad. Now, I would like to demonstrate monads to you, but in order to do that, I need to switch representation. I need to go functional for a little bit. And I would like to introduce you to monads through closure. Does anyone program in closure? 2, 3? Great. So for the rest of you, you don't really need to know closure. What we're going to use is really, really simple. And I will walk you through it all. So this is the C# code where we started out. Now, let's see how that code translates to closure. You will see that, yes, it looks a little bit different, but that's basically just because we have a different naming convention in closure. The code is virtually identical. The only difference is we have a keyword over here called let. And let is just something that allows us to introduce symbols on the left. And just as in C#, those symbols are bound to the result of computations on the right. And just as in C#, the flow of control goes from top to bottom. And just as in C#, as soon as something returns null, the whole thing blows up. Let's see how we can introduce monads into that code. So here's our starting point. This is the closure code I just showed you. Now, to introduce monads, we really just have to change one single line of code. Here's that line. So the only thing we have done now is that we took let here and replaced it with doMonad identity m. DoMonad isn't that interesting. That's basically just syntactic sugar that knows how to apply a monad. The interesting thing is the monad itself, and that's the identity monad. Now, the identity monad, you can think of it as, you probably all know the function identity. Whatever we send it, we get the same thing back. So identity monad glues together computations by just passing the values through. So if identity monad gets a valid value, that gets passed on to the next stage in computation. If an identity monad gets null, it passes that on as well. So the whole thing still blows up with a null pointer exception, but now I would claim that we have all moved a step forward, because we have found a way to run code between each computation. And the only thing we have to do now is to take our maybe monad and replace it with a different monad, an optional type checker, the maybe monad. So the maybe monad here, it behaves a bit differently, because maybe actually looks at its argument. So if maybe receives a valid value, maybe will pass that on. If maybe receives null, maybe will short-circuit the rest of the evaluation. And we are safe for any null values in this code here. And the power, to me, of monads is that if you look at this code, you see that we're basically just changing one single word, and we get a radical different behavior. And that's real power. And the reason that we get that is that what we have done here with monads is that we have actually separated the knowledge of computations from the knowledge of how to glue them together. And this, my friends, that's separations of concerns for real. Now, I've given versions of this talk earlier, and when I do that, I normally go into how you can implement this stuff in C#. But I don't want to do that today, because this is the first time I do a 90-minute session about it, and 90 minutes, that's a long time, and I don't want us to get lost in details. I want us to stay and look at the overall patterns here. And besides, not everyone is interested in C#, but if someone is, please talk to me afterwards. I'll be staying around for the rest of the conference, and I'll be happy to show you. And you can basically do the same thing in Java as well. So what I want us to do instead is to get our oxygen flowing again. And we're going to do that by doing a small experiment together. And it's an experiment that will teach us something about the brain. So please, everyone, stand up. I promise you, it's well worth it. Now, take your left hand, it's quite suitable in here, and put it in front of your face. Now, wiggle your hand as fast as possible. You look amazing. Thanks. Please sit down. Now, did you all saw that? As you start to wiggle your hand like this, it's like you see multiple copies of your own hand, right? But I mean, I still just have one hand here. So what are those copies? Well, it turns out, and I told you earlier that our human brain, we have different memory systems. One of those memory systems is actually a sensory memory buffer. So all your visual information, it gets gathered in a short-term store. And it's short-term, it's really just like a few hundred milliseconds. So those multiple copies of your hand, those are actually echoes from your short-term visual store, the iconic memory. Now, you have the same type of short-term storage for audio information. And in fact, while visual information is just stored for a couple of hundred milliseconds, audio information is stored for much longer, 3 to 4 seconds. Why do you think it's longer? It's because we should be able to comprehend words like this, which actually is the longest word in the works of Shakespeare. And it means something like the state of being able to receive honors. And yes, I had to look that up. So, there's a lot of interesting things going on in our brain. And those short-term memory stores, we actually met them when we talked about attention. Remember the cocktail party? The reason the cocktail party effect works is because your unconscious processes, they are scanning those short-term memory buffers. And it turns out you take in a lot more sensory information than what you're consciously aware of. Most of the information you take away is just thrown away. And you only experience that information that you're consciously aware of, that you focus your attention on. And this can get us into a lot of different troubles. And I would like to show you a really good experiment on that. And this is such a well-known experiment, so I think that some of you have probably heard about it. How many of you have heard about the invisible gorilla? 10 maybe? Cool. So the invisible gorilla experiment, it's brilliant. What researchers did here was they showed participants a short movie on 2 basketball teams. And the task for the participants was to calculate the number of passes between the different players. Now, it's a simple task, but it requires you to constantly focus your attention, right? And the psychological twist in this experiment was that sometime in the middle of that short movie, a man dressed out in a full gorilla suit walks across the basketball field like this. And, I mean, it was a test on attention, right? So if something surprising like that happened, I'm pretty sure that you would notice, right? You don't really expect to see a gorilla in a basketball field. So surprisingly, it turned out that 50% of the participants failed to see the gorilla. And when the researchers told them afterwards, the participants were surprised. I mean, how can you miss a gorilla? It's quite amazing, isn't it? But it turned out, and this is a phenomenon called inattentional blindness, that we can only focus our attention on one single thing, as we talked about earlier, right? So we're focusing on calculating passes, and during that time, even if we somehow see the gorilla, I mean, we don't really see with our eyes. We take in the sensory information, but we see with our brain, and our brain has its attention focused elsewhere. This can happen. Inattentional blindness happens in programming as well. And you've probably all experienced this. It's an old thing. It's well known if you've been programming for a number of years that you sit there and you have this tricky problem and you really don't know how to resolve it. So you ask a coworker. Your coworker comes along, and as soon as you start to explain the problem, you just, aha, that's the reason it doesn't work. Thanks a lot. Yeah, but I didn't say anything. Oh, no, thanks. Right? And in fact, we don't even need a coworker, and this is why this technique is referred to as rubber duck debugging. It's enough to explain it to someone. It's the very act of explaining, and we don't even need a human being to explain to. And the reason for that is that when we try to explain something, we take a different perspective. And that different perspective allows us to focus on our attention on different details, right? And that allows us to detect if there's a glitch between our mental model of the program and what we actually see on screen. So I use rubber duck debugging a lot. But it's also an after-the-fact technique. It's something we use when we already have a problem. What if we could somehow get a different perspective on our code while we're writing it? I would like to show you a simple way to do that. There are several ways, actually. But before we do that, I have to make a small confession, which is quite suitable in here, actually. I, Adam Tornhill, I have been using code coverage metrics. The reason I don't talk about code coverage metrics anymore, I've been using them for 15 years now, and the reason I never talk about them is that as soon as you mention that you're measuring code coverage, some manager comes along and says, oh, we need 80% coverage. No, you don't. Perhaps you need 95, or 10, or none at all. Without context, it's really just a number. Context is everything. So that's the reason I never talk about code coverage, but I still use it. But I use it in a different way. And the way I use code coverage is like this. I typically never bother with coverage until I've written the first version of a program, but then it gets interesting. What I do now is that I look through the lines that I haven't covered with tests, and I try to understand why. Because this gives me the opportunity to do an implicit code review on my own code. And from a different perspective, from the perspective of the coverage, right? From the perspective of the tests. So sometimes there's a good reason why I haven't covered that line. I know why it isn't covered, and in that case, it's okay. But more often than not, I notice that my mental model of the program didn't fit reality. So this is a really simple thing to do, and I recommend you all to try it out. An implicit code review by yourself is really useful. And I would like to continue on this track and talk a little bit about culture. Now, culture is important because beauty has a strong cultural component to it as well. And you can pretty much witness that here. This statue here, that's Venus aus Willendorf, a famous statue exhibiting a 20,000-year-old fashion. And beauty has a strong cultural component. You know the things I told you earlier about beauty being a mathematical average, beauty being the absence of ugliness. That's true across the whole globe. It's true in virtually every culture. What tends to vary are the things that we can affect ourselves. I mean, for example, take our body. So if I want to, I can become bigger. And if I want to, I can also become thinner. Those are the things I can affect myself, and those are the things that tend to be the cultural component of beauty. And you can pretty much witness that. You don't even have to go 20,000 years back. Just pick up some fashion magazines from the last 30 years and witness how the view of the male and female body has changed during that time. It's actually quite dramatic. And that's the cultural component of beauty. We have a strong cultural component in our development culture as well. And I became quite aware of that last year. Last year, I started to learn a new language called J. And J is a language in the array language family, where you have already seen APL. You have languages like J, K, Q, and you realize there went a lot of creativity into the naming. But the way I approach it is, when I'm about to learn a new language, I always start by looking at a lot of existing code in that language. Because I think that makes for a pretty nice mental preparation. You know what lies ahead of you. You know what to expect. So I did the same thing with J, and the way I did it was I went into Rosetta code and looked at a bunch of different problems and solutions in J. And one of the coolest problems was this. The task here was to print out the name of the programming language in ASCII graphics in 3D. And that's actually, I like it because it's doable, but it's not simple. So there were a bunch of really cool J solutions. Things like this, where you see the J logo slightly rotated. Then there was another solution where you see the J up front. And I think that one is pretty cool as well. Now, I would like you to ask you to do this. Think of your favorite programming language, the language you are the most productive in. how many lines of code would you need to print out those logos? And I know, we were all at the keynote yesterday, so I know that there's no estimates. That's really the thing now. But anyway, I want to ask you for an estimate. How many lines of code? 1,000, anyone? Who could do this in 1,000 lines of code? Oh, cool, 500? More, less? Come on, just give me a number. How many? A lot. Cool. A lot. That's a pretty good solution. I'm happy with that. So let me tell you this about J. J is a very compact language. So in fact, this solution here is done with just 36. 36, that's really not much. It's not a lot. And I'm not referring to 36 lines. I'm talking about 36 characters. Here's the complete code. And I know what you think. The first time you see J, it's really like a cursing cartoon character, right? But let me tell you this. I won't claim that I understand everything. But as soon as you start to learn J, you will notice that there's a lot of intrinsic beauty inside it. There's a lot of consistency. And J also lets you get rid of all that nasty stuff like explicit conditionals. It's a truly beautiful language. What's interesting from a cultural perspective is, again, let's look what's absent. Today, I do most of my work in a .NET environment. And in the .NET culture, we value things like long descriptive variable names, right? To a J programmer, a long descriptive variable name, that's really just line noise. We don't need it. And that's, I think the interesting thing is how a different context, in this case, when your complete program fits on a single line of code, the whole environment, the forces are different. And you come to value different things in that culture. To a J programmer, a long descriptive variable name, that's really just something that distracts from the things that actually do something. And when I started to think about that, I came to think about a famous psychological principle called a mere exposure effect. Now, the mere exposure effect, that's basically that the more often you see something, another person or an object, the more you like that. So the more often we see something, the more we like what we see. Again, I think that the mere exposure effect probably has evolutionary roots. I mean, think back to a time where we lived in small tribes or small villages. The people around you or the objects around you, they were probably quite important for your survival, right? So it kind of made sense that we liked them and cared about them. What surprised me about the mere exposure effect is how strong it is. And there's a really good experiment to demonstrate that. What the experimenters did here was that they presented the participants with Chinese characters. Now, the participants, they were Western Europeans and Americans. They didn't knew Chinese. So they got to see two different characters at the same time, and their task was to pick the most beautiful one. Of course, there was a small psychological twist. Just before those characters were shown, one of them was flashed really, really fast, 50 milliseconds, which is so fast that you are not consciously aware that you have seen anything. But it's slow enough for your helpful, unconscious brain to pick up the information. And it turned out that 50 milliseconds were enough to bias our sense of beauty. The participants preferred the character they had seen before, even if it was just for 50 milliseconds. And I think that's quite amazing how strong that effect is. So let me ask you this. If 50 milliseconds is enough to bias your sense of beauty, what do you think happened when we spend 8 hours a day looking at the same kind of code, day in and day out? So this is one of my most important recommendations. Don't confuse familiarity with beauty. And I think that the best way to avoid that is by learning different languages and different technologies. That gives you a radically different cultural perspective on what you do in your daily work. So let's move on to talk about context. And I told you this when I started, that I think that psychology has a lot to offer to us developers. But when you start to study psychology, it's actually quite a scary experience, because you start to doubt yourself. You start to realize how limited we humans actually are. You see flaws everywhere. So, for example, when I started to study cognitive psychology, I realized that this programming stuff, it's actually way too hard for us. We shouldn't be able to program. But yet, we do it. And the reason we do it is that, yes, we humans, we have a lot of cognitive bottlenecks and limitations, but we are so good at coming up with workarounds. And I would like to tell you a little story about that. But first, I would like to ask you something. How many of you would like to have a better memory, be able to remember more? So that's virtually all of you. Please keep your hand up if you would like to have a perfect memory, never be able to forget anything you learn. I would like to have that. It's cool. All right, not so many there. So let me tell you a little story about a man with a perfect memory. This guy here, that's Alexander Luria, and he's a famous, was a famous Russian psychologist. And Luria is quite famous for his case studies. And one of the case studies that he did was on a man with a perfect memory, a memory expert. And that man, he used to earn a living by performing at different shows and markets. So he traveled across the country. And one thing that he typically did was this. He did something quite similar to what I do now. He stood in front of an audience, and then he asked everyone to please shout out random numbers. So people started shouting numbers like 117, 93, 13. And behind his back, someone was scribbling down all those numbers. And when that was full, like say they had 100 numbers, the memory expert, without looking at them, repeated every single number from the beginning to the end in the correct order. And if you just paid him a little bit extra, he could do the same thing in reverse. So that's actually quite impressive, isn't it? But let me tell you this. Everyone inside this room would be able to learn this trick. I mean, it's hard, but we have a lot of good strategies to be able to remember random information like that. You just have to practice a lot, but it's definitely doable. What I think is hardly doable is what happened next. Luria, he took part in all those shows. So he used to write down all those numbers that were presented. And one day, he decided to do something differently. He decided to test the memory expert on something old. So he said to a memory expert, "Do you remember that time we were in Moscow?" And the memory expert, he went like, yeah, sure. That were the time when we had the numbers 117, 93, 13. He could remember every single number he had ever heard, even if they went 10 years back. That's quite impressive. And when I read about this case study, I mean, that was done back in the 30s. And when I read about it, I started to think, what if this guy was a programmer? What would be different? How would his programs look? So I started to think about it and think about what would be different. I mean, long descriptive variable names, not really necessary. He can remember the purpose of every single variable. So why not go with single-digit letters? It's the simplest thing, right? Immutability, encapsulating side effects. There's no need for that. He could remember the precise order of execution. He knows where the side effects are. There's no need to do that. But I think that it's quite easy to get blinded by the advantages of a perfect memory and forget about the limitations it has. Because one of the things with this guy was that since he had a perfect memory, he never needed to learn those workarounds that the rest of us have. So one of the workarounds we use for our imperfect memory is abstraction. Because abstraction literally means to take away. When we're abstracting, we're trading details for convenience, right? And this guy, he never learned to abstract. So as a consequence, he had a terribly hard time to reason about abstract concepts, like nothing. He used to visualize things. How do you visualize nothing? I don't know, and our memory expert didn't know either. But we programmers, we're pretty good at abstractions. And I think we can take it one step further. I want to show you a simple example on that. So this is some code here. We have two methods, and we see that the variable names here, they're actually pretty good. We have a language ID, and we have a news item ID. But have a look at the types. You see that both the language ID and the news item, they are of the same type. They are an integer. Are they really the same type? I would say that a language ID is something completely different from a news item ID. So what I do when I see something like that is that I introduce simple domain types. And I guess that's something that all of you already do, but it's such a useful thing, so I want to show you that anyway. So the way I do it is that I take the code and I introduce simple domain types like this. So you see, instead of integers, I now have a language type and a news item type. And the cool thing with that is that when we start to express our domain in our type system, our variable names get free to use for different purposes. So we can use them to communicate context. So now, this isn't just a news item, this is the clicked item. So this allows us to communicate so much more information. And for me, this is the big win when it comes to static type systems. It's not just about early compile time checks and perhaps better optimizations and stuff like that. No, the big win with a static type system is that it allows your programs to communicate more information. So please, put your domain in context. Your brain loves that. All right, I'm going to move on to talk about representation. And representation, let's take a step back there. Representation, what I mean by that is that programming, to a large extent, is problem solving, right? So what you see here is a model of human problem solving. And this model is taken from the field of educational psychology. And the reason I do that is that I think that we, as developers, we face much the same challenges as educators do. We need to communicate knowledge through time and space to the poor maintenance programmer coming after us. So here's how that model works. It's based on two mental models. The first one is called a situation model. And the situation model, that's basically everything you know about the problem you're trying to solve. So what you do when you develop is that you take all that knowledge you have about the problem and you express it into a system model. The system model, that's everything you know about the solution, your code. So when you express your domain knowledge in that system model, you also observe the outcome, and you learn from that. So you get feedback from your solution. And that feedback, in turn, helps you build your situation model. So those two models, they co-evolve. And the takeaway is that programming, first of all, it's a learning activity. We learn by doing and by observing the outcomes. And second, programming is also an iterative process, because human problem solving is an iterative process. And there are a bunch of conclusions you can draw from this. First of all, I think that it should have an impact on our environments, our coding environments. We should never be satisfied with environments that don't allow us to iterate fast between our situation and system models. It's vital to our task as problem solvers. And I could probably do a talk around that as well, but I want to focus on a different aspect of this model. I want to focus on the language aspect. Do you remember Ludwig Wittgenstein, who said that the limits of my language means the limits of my word, right? I think that's relevant here, because if we look at this model again, we see that it actually gives us a way to define what good design is. Because it turns out problem solving gets easier the better aligned those two models are. The better aligned they are, the closer together, the easier it is to iterate between them. So that's actually a good design. And the challenge to us as developers is to take our low-level, general-purpose programming languages and lift them up to the level of the problem. And this is indeed a challenge. And I would like to show you two radically different ways of attacking that problem. So let's start at the wrong side of the spectrum. Let's start where you don't want to be. Let's start with brainfuck. Brainfuck is a really interesting programming language. As far as I know, it's the only language with the design goal of being deliberately hard to learn. But brainfuck, what you see here, that's hello world in brainfuck. Now, the interesting thing with brainfuck is that it's not hard in the way that, say, C++ is hard. Brainfuck is indeed quite a minimalistic language. You just have something like 7 or 8 operators to learn, and I promise you, if you spend 20 minutes reading up on the syntax, you will know everything there ever was to know about brainfuck. And you can sell yourself as brainfuck experts. How cool isn't that? So brainfuck itself is quite simple. The reason it's hard to program in is, again, because something is absent. We don't have any way to introduce chunks. There's no way to name our concepts. We cannot put labels on things. And that means that brainfuck programs puts a terrible cognitive load upon our mind. Of course, that hasn't stopped people from doing really interesting stuff in brainfuck. And this is one of my favorites. It's done by another Swede, and what he has done is that he has programmed Conway's Game of Life in brainfuck. And I would claim that even though this program, to a certain extent, is self-documenting, I wouldn't claim that it's a good match between the system model and the situation model. Because take everything you know about Conway's Game of Life. No, there's really no alignment there, right? So what happens with brainfuck is basically that we widen the gap. It gets harder and harder to iterate between those two models, and problems are, as a consequence, quite hard to solve in brainfuck. So let's look at the other side of the spectrum. Let's look at a somewhat more productive approach. And I would like to do that by introducing you to domain-specific languages in Clojure. And this time, you actually need to know a little bit of Clojure. So this is my 20 seconds introduction to domain-specific languages in Clojure. And after that, you will know everything there ever was to know about domain-specific languages in Clojure. Promise. So here it is. You see in Clojure, let's look at some data types there. As soon as you put parentheses around something, you get a list. So this is a list with 3 elements, the digits 1, 2, and 3. If you instead put square brackets around something, you get a vector. So this is a vector with 2 elements, sum and data, those 2 symbols, and they in turn may refer to either primitives or perhaps other containers themselves. But this is basically all you need to know. And let's see why. Let's have a look at the code that we wrote earlier when we talked about monads. So the first thing you notice here, and that's quite interesting, is that the code has parentheses around it. It's actually a list. And inside that list, you will find a bunch of square brackets. Oh, it's a vector. So Clojure has this interesting property, like all Lisp-based languages, that the source code is expressed using the language's own data structures. Clojure is meta-circular. And that means we can actually write programs in Clojure that operate on our own source code and transforms the source code. And it's a simple thing to do because the source code itself, that's the data structures that were used to work it. So we can use the same operations and the same standard library stuff to do that. So this makes Clojure a very good fit for domain-specific languages. And I worked on that a couple of years ago. And here's what we did. That was some work in the air traffic control industry, and we needed to integrate with the radar station. Now, if you work in the air traffic control industry, you're pretty much familiar with asterisks. And asterisks, that's a communication standard. And as you see here, you see an example of 2 asterisk messages. It's a fairly low-level protocol. It's a binary protocol, and it has a bunch of really tricky encodings. So let's see how those asterisk messages actually look. Here's the content of them. And you see that every message has a category. You have a bunch of different timestamps. You have different coordinate formats. You have vectors, and you have floating points, and all that kind of tricky stuff. So when we started to do this work, our task was to interpret and present things like that in a human-readable format. And I was like, no. There's no way I'm going to write a parser for that. I really don't want to do that. So what we decided to do instead was to introduce a domain-specific language enclosure. And what we did was basically this. We took the asterisk specification, and this is the actual standard. That's how it typically looks. So you see you have a bunch of different data fields, and each field has a length, and you also have a data item over here that kind of specifies the encoding for each one of those fields. So what we did was basically, we took this specification, put parentheses around it, and made it compile. Here's how it looks. So this is the closure code, and that code, when it's compiled, actually generates a bunch of different parsers and presenters that are actually able to do that interpretation I showed you earlier. Now, I won't claim that this is a perfect example of a domain-specific language. But what I will claim is that I think that this is a pretty good alignment between our situation model and our system model. And the advantage here is that we can basically take everything we know about the standard, everything we know about the domain, and apply it to reason about the solution as well. So it's quite easy to iterate between those 2 mental models. And that means we can actually move away from instructing a machine to expressing a domain. So we have arrived at our final topic of today. And now I want to rant a little bit about the environment. I'm not going to talk about global warming and stuff like that, no. But I'm going to talk about an almost equally big disaster. And it's a disaster that affects us all. I'm going to talk about our office environment. So how many of you have read the book Peopleware? A few of you. It's a book I really recommend. I think it's the best book ever written on the people side of software. And my favorite part of Peopleware is this. They have done a really huge study on noise in the workplace and how it affects us. And they have studied virtually hundreds of companies over decades across the globe. And what they found out is quite interesting. They found out that individuals in quiet working conditions are much more likely to deliver zero-defect works. And to me, this is so fundamental. This is really a no-brainer. If you run a business and you want a way to dramatically improve your quality, that's like one of the best problems to have. Those kind of problems, you just throw a little bit of money on it and it goes away. You just need to provide quiet working conditions, and a lot of your defects goes away. I think it was something like a 30% difference just because of office noise. And I really don't understand why that doesn't happen. The consequence is that a lot of us developers will need to work in noisy work environments. But again, we are developers, so we are pretty good at workarounds. What workarounds do we typically use? Perhaps something like that. We listen to music while we code. And I've been doing that myself for decades. And then one day I start to think, I'm listening to music all day long when I code. Perhaps it affects my performance. So I started to study the subject. And what I found was quite interesting. So let me tell you right away that music will affect your performance. How many of you think it will have a negative impact? Maybe 10 of you? And a positive impact? Also something like 10 of you. So Let me tell you this. This is such a nice conference, and I want you all to feel good. So guess what? You are all right. Yes, music will affect your work, the quality of it, but the direction of that effect varies with the task. And the first studies that were done on music in the workplace were done back in the early 40s. That was the blue-collar industrial worker era. So you have assembly line workers, and I mean, their work, it was pretty monotonous. It wasn't particularly fun. And when they introduced music in that setting, the productivity actually rose. And in addition, the workers themselves, they reported feeling better, because now their hours passed by faster, so they enjoyed work a little bit more. But software development is a bit different. Sure, if you look for a way to get through a monotonous, boring task, by all means, just listen to music, pick your favorite tracks, and it will make you produce that task a little bit faster and help you feel better in the process. But when you code, that's a bit different, because first of all, it's a motivational aspect. Our work isn't monotonous and boring. In fact, most of us developers, we are self-motivated. And that's the reason that we attend conferences like this. We want to improve. We love what we do. And in addition, we talked a lot about this today. We just really have one thing that we can be consciously aware of at a time. So when you listen to music, music will compete for your attention and draw away cognitive resources from your code. So when you listen to music, you will pay a price. So what do? Well, it turns out, if we want to perform at best, and I'm really sad to say this, I really wish that I would come to different conclusions, but I can't. If you want to perform at your best, there's really no substitute for silence. You need quiet working conditions. It's important. If you can't get that, music becomes a decent workaround. It's much better than office noise, so continue to use music in that case. But I would like to give you a few recommendations, because all music isn't equal. And it turns out that the brain processes lyrical and melodical content differently. And the words, they compete much more for your attention. So you really should prefer instrumental music, or maybe, if you like, colored noise. Those two are virtually identical. There's more to it. Music also affects your emotions. And as soon as your emotions are affected, your attention suffers. So that means you have to avoid music that you strongly like. So that means no Yellow Submarine in the workplace. Obviously, you also need to avoid music that you strongly dislike, so just say no to Justin Bieber. But used right, music is a useful noise reduction technique. So I'm almost done now, but before I leave you, I want to tell you a little story about the anatomy of the brain. Our human brain, as you all probably know, is made up of two halves, two hemispheres, one left and one right side. And our mental functions are a bit unevenly distributed. For example, language. Our language tends to be located in the left side of the brain. And those two brain halves, they communicate via a thick fiber of nerves called the corpus callosum. What do you think happens if we decide to cut that connection between the brain halves? All right, this is not some kind of crazy Frankenstein experiment. This is actually a medical, historical procedure that's been done on epileptics to stop the spread of this disease, to help them. And what happens is actually that when you cut the corpus callosum, you end up with a person with two smaller brains within the same head. And it's not as drastic as it sounds. Those patients, those historic patients, they are called split brain patients, by the way. If you meet one of those split brain patients, you probably won't notice. They function pretty well. But the scientists, they love them. And they love split brain patients because it gives them more opportunities to study the differences between the left and the right side of the brain. And one way that they typically do it is like this. They have a split brain patient, and they ask them to please sit down. So the split brain patient sits down, and then they instruct the right side of the brain part without the language center to please stand up. So the split brain patient rises. And now the researchers ask them, why did you stand up? And now the left side of the brain with the language center takes over and answers things like, you know, I got thirsty, so I decided to go for a glass of water. They don't answer, which would be much more appropriate. You know, my brain holes, they have no connection between them, so I really don't know. No, they make an after-the-fact rationalization. And in fact, that's the way our brain works. Our sense of self, our sense of free will, it's just an illusion. Our sense of free will is an after-the-fact rationalization. It's an illusion. And the takeaway for us as human beings is that we can all be deeply skeptical about who we truly are. And the takeaway for us as programmers is that we can really question, who writes your code? And the reason I'm telling you this is because I want to point out that this is a vast topic, and this presentation has really just scratched the surface. There's so much more that I had to leave out. For example, I had to leave out all the stuff from social psychology, how we work together, how we make decisions in groups, and how we influence each other. And I think that most of the time, those factors are more important to our software projects than the technology that we use. I also had to leave out all the personality stuff and the individual stuff, and I think that will be interesting to look into as well, because we humans, we differ a lot in our cognitive abilities, and it will be interesting to see how that changes how we approach programming. So I hope that I will be able to talk about this stuff at some presentation sometime in the future. Until then, I really just want to say thanks a lot for listening to me.